Moving on to some more examples of horizontal motion. And these two examples, you need to appreciate that there's a system in place where there is a ring that is able to move anywhere along a string. You may have one string, you may have two strings, and we'll talk about both scenarios. So this first one we're going to explain here. We have one piece of string, and threaded through that piece of string is a ring, and that with a weight, with a mass, and that ring can be moved somewhere along that string. The string is held in place and anchored in both ends. So the ends A and B of a light inelastic string, a CB of length 80 centimeters, are attached to fixed points. So there's a point sort of fixed above and then a point fixed below. They tell us that point A is 40 centimeters vertically above point B. A ring of mass 2 kilos is attached to the string. When we say attached, I see the point here is it's attached, it's threaded through, to be more precise. Okay, it's positioned at a point C along that string in such a way that the triangle that's made A, B, and C, where the string is only along AC and CB. The string is not going along from A to B. Okay, that's just empty space in that section there. Anyway, the angle is made between point B, and point C of 90 degrees. Okay, the ring is made to describe a horizontal circle. So C is moving around in a circular motion horizontally. And the radius is R. So we can immediately appreciate the distance from B to C is that the radius of the circular motion. So appreciating the relationship of those 3 points, it tells us the distance between A and B is 0.4. It tells us that the distance between B and C, well, we don't know. We appreciate it's the radius of the circular motion. And the distance from A to C to B in total is 80. So if we call BC R, we can appreciate that AC, we can describe that as being 80 minus R. Now, I'm sticking to using meters here rather than centimeters. You could just call that the AB 40 and AC being 80 minus R. Like it doesn't really matter. I suppose once you get to the point where you get your R, you're going to have to make sure that when you apply it and use it, you're going to think of it in meters. Okay, so we can use the application if that's a right angle triangle, as stated in the question. Then we can use Pythagoras. So we have 0.8 minus R, all squared, the hypotenuse squared, is equal to the two other sides squared and added together. So R squared plus 0.4 squared. And multiplying out those brackets, we end up with the statement, and tidying it up, we end up with 0.48 is equal to 1.6 R. And we divide that, we are going to get 0.3. And as you can see there, if I had chosen to take 80 and 40 as numbers, I could have worked through that same algebraic process, probably actually more easily because it didn't involve the decimals, and I've got my value for R as being 30. But the key thing is, you can see in a little while, we're going to need to use the number 0.3 in our calculations. So let's now concentrate on the actual motion of the object and the forces that are acting as a result. So we have these two parts of a string. Draw a line straight, and on that string there is a weight that's hanging through it. There is tension in both directions. Remember, if you've got one piece of string, then there's one tension occurring within inside that piece of string. you'll see in a separate question we'll do in a moment where there's two different strings with two different tensions. But there's one singular tension, T. There is a weight. Now it's 2 kilos, so therefore it's a weight force acting down of 2G. We have this angle here of alpha. That is also the angle that's occurring from the horizontal, the vertical to the this part of the string that is at an angle. And we can get a description for that angle alpha if we appreciate the measurements we found for that right angle triangle. It was we knew 40, it was given 30, we found out, and we're realizing it's a 3, 4, 5 triangle. Okay, so it doesn't take too much to realize that the sine is going to be 3/5 and the cos is going to be 4/5. So with that horizontal circular motion, we appreciate that the forces acting vertically must basically cancel each other out. Forces up equals forces down. So we can take the component of our tension here as being T cos alpha. We'll also appreciate the horizontal component of T is going to be T sine alpha. We'll deal with that in a moment. So just dealing with that vertical, so T cos alpha is going to equal, in the opposite direction, the 2G. We know what cos alpha is, it's 4/5. So we get 4/5 of the tension is equal to 2G. And as a result, we can work out what that tension actually is, because we know what G is, it's 9.8. So 2G divided by 4/5. And we end up with an answer of 2.5G, which is equal to 24.5 newtons. As we progress, it doesn't really matter whether you use the 2.5 G, 5/2, lots of G, or whether you use the 24.5. To be honest with you, at some point in time, you're going to probably need to substitute 9.8 in, but you might choose to leave it until later on when you've got an expression for G. It's up to you. Anyway, so that's the vertical forces. So if we then look horizontally, we understand force equals mass times acceleration. We understand the centripetal force, okay, is going to equal to mr omega squared. So the forces is the force pulling it in. So we appreciate that there's two parts to that. We've got T, that's the force that's, let's choose a different color, that's that T that's here, from the bit of string that goes to point B. And then we've got the other force, which is the T sine alpha, which is the component of the tension of the string that goes up to A. So we end up with T plus T sine alpha. That's the sum total of the centripetal force. That's going to equal to mass times by radius times by omega squared. So let's just fill in our values. So T is 2.5 G. Now, we've then got the sine of alpha is 3/5. The mass is 2. The radius is 0.3 in meters. And the only thing we don't know is omega. The left-hand side sums to 4G and the right-hand side is 0.6 omega squared. So we can work out omega squared as being equal to 4 times by 9.8 and divide by 0.6, and then we can square root that answer. And so we get an angular velocity omega of 8.08. So we've worked through, we found the radius of the circle, we then found the tension in the string. Okay, just bear in mind, that the tension is the same throughout that string from A all the way to B. So we had just a singular T to describe that tension going in both directions of the string. And we then finally worked out the angular velocity of the string. Correct, 2 decimal places. Moving on, we have another question here. This is a bit more complicated and we'll talk it through. So we have a vertical rod. Now just wait, the diagram you can see here is slightly lopsided. That's because of the scanning that I did. That PRQ should be vertical. Okay, so the rod PQ of length 10L is fixed to a horizontal surface at Q, just it's standing up basically, and the other is P is vertically above Q. As I said to you, PQ is supposed to be vertical, sorry. The ends of a light inextensible string of length 10L are fixed at P and R, a distance of 6L below P on the rod. So R is 6L below P. A small mass M is tied to the midpoint of the string. Now this is really important to appreciate. This is not a ring anymore. This is actually literally tied to it. Okay, halfway along, and it rotates with both parts of the string taut in a horizontal circle with uniform angular velocity W. Find the tension in each part of the string. So you have to understand here that there are two different tensions occurring on this string. I know it's one single string, but you can imagine it's actually, you've got a mass, okay, and two strings coming out of that mass of equal length, okay, and those two strings, the string that goes to P and the string that goes to R, are two different strings and will have two different tensions. So the way in which the question is worded can lead you in the wrong direction. You have to appreciate that because that mass is not freely able to move along the string, it's tied, it creates effectively two different strings, and they will have two different tensions. And then at a certain instant, both parts of the strings are cut simultaneously, so there's other things going on. So we'll worry about that second part in a moment. We'll concern ourselves with part one, which is looking at the motion that's occurring. So if you break down this question and kind of concern ourselves with the lengths, so the distance between P and R is 6L. The mass, which we'll call point M, is halfway along the string. The string was 10L in length, so basically the two parts, two different strings is 5L and 5L, and we've got a symmetrical shape there, an isosceles triangle effectively. Okay, so and the radius of the angular motion is that distance from M to the perpendicular distance from M to the line PR. So straight away, the 3, 4, 5 triangle is screaming at you. You shouldn't need too much work on that one. You should realize very quickly using Pythagoras that R is going to be 4L. And if we appreciate the angle with the vertical, which is going to be the same for both sort of angles, angle at P and the angle at R. Let's call it alpha. We've got the sine is opposite over hypotenuse, which is 4L over 5L, and the cosine, the adjacent over hypotenuse, is going to be 3L over 5L. So we've got 4/5 and 3/5 for the sine and cosines of that angle, and we can appreciate that that alpha occurs effectively from the mass as well. We can realize that that angle there, alpha, occurs in those two positions at M. So we have two tensions. We have the tension going towards P. Okay, I'm running out of space here on the diagram of T, and the other tension we could call S. You could do T1 and T2 as well if you wanted to. So T and S are the two tensions coming out of M, and we can appreciate the mass M. Okay, now it has a mass of little m, so therefore the weight of it is mg. And those two tensions are creating an acceleration in the direction towards the center of that circular motion. We can appreciate the sort of moving around in a circular motion. And the acceleration, the centripetal force is acting towards the center. So let's use the same process, work out the vertical forces occurring, and then separately the horizontal forces, and we can hopefully work out the two tensions. Now, straight away, if you appreciate there are two tensions, we've got two unknowns, you can sense that we probably need two equations with two unknowns to be able to resolve this matter. So if we think about the vertical forces occurring, so the tension T is equal to, in the vertical is T cos alpha. Okay, so that works out as being 3/5 of T. And then we can appreciate that sorry, I just realized I put the wrong letter for the tension. It should be S. And going downwards, that second string going downwards, it's going to be S cos alpha. So that tension there is going to be, again, 3/5. This time it's S. We also have mg. So going up, okay, we've got 3/5 of tension, and going down, we've got 3/5 of the S plus the mg. And then I suppose if we multiply everything by 5, we end up with 3t is equal to 3s plus 5 lots of mg. And so that's one equation involving the two unknowns. I know m is an unknown as well, but we're just working this through in terms of mg. So t and s, the unknowns. So we'll now look horizontally at the forces acting horizontally, and they are therefore going to be the sum total is going to be the centripetal force. So if we take the two forces acting towards the center from the object, you've got t. Sorry, let's just write that way around. Sorry. So we got T sine alpha, and we've also separately got S sine alpha. Though both those together are acting sort of or towards the center from the mass. And no other forces are occurring, so we end up with the centripetal force. This is horizontally. We have T sine alpha, so that's 4/5 of T. And we've got S sine alpha, so that's 4/5 of S, and that's the sum total of the forces, and that is equal to ma, so mass times acceleration, so mass times by the radius times by omega squared. And if we appreciate that the mass is m, now the r is 4L. Omega squared, we don't know. If we multiply everything by 5 as our next sort of task, we end up with, well, actually maybe I just leave it open, not factorize, leave the 4 there. So multiply everything by 5. Hang on a second. Let's just hold your horses, Robert. Hang on. Let's go back a step. So I'm noticing that 4 is a common factor on both sides. So I'm going to multiply everything by 5. So I end up with just T plus S is equal to 5 lots of mL omega squared. So we have two equations, and it's a case of doing some work, simultaneous equations work on these two equations. So setting yourself up for simultaneous equations, we end up with 6t being equal to the sum of 5mg and 15 mL omega squared. So if we divide by 6, we end up with 5/6 of m multiplied by g plus L omega squared. Hang on, there should be a 3 in there. 3L omega squared. So I've taken out 5 as a common factor, m as a common factor, and I've divided by 6. So 5/6 of m multiplied by g plus 3L omega squared. And that is, to quote, the tension of the string in terms of m, l, and omega for the tension going up towards P. We now have to do a similar process to work out the tension going towards R. So we need to work out what S is, and that's a substitution process. So substituting that in for t, we end up with 5/2 lots of ml omega squared minus the 5/6 of mg. So if I'm running out of space here, but if I want to, again, to factorize that a little bit, I end up with 5/6 of m multiplied by 3l omega squared minus g. Now, if you don't mind, I'm not going to bother doing part 2. It's actually a projectiles question, and I'm not going to concentrate on that today. We've done projectiles. We don't need to concern ourselves with that for the moment. Okay, so if I could just briefly speak to you lastly about one final scenario, which there is a worked example in the book on page 131 looking at this. But I'll just mention it very quickly. Imagine what we discussed there a moment ago, where we had the string, and so let's just draw this out. And we have a mass at this point in time here, creating a weight. Let's say we had, there's a mass there, and there's this piece of string that's fixed at this point in time up the top here. But at R, it's not fixed. It's actually, imagine there was I suppose a pole going down all the way down, and actually there was a ring here. Okay, so it wasn't fixed. It was a freely moving ring. Then what's gone on in that instance? So let's just get rid of that line. Imagine there's that ring is fixed in terms of the vertical, okay, below P, but it can move around. So, and it in itself has a slope of, sorry, not a slope, a mass of m, and it's going to have therefore a weight of mg. So what's occurring in this scenario? So let's just talk briefly about the various different forces acting. So we have our tension going up towards P. We have tension going towards R, which is S. And we have our weight mg. So the T, again, can be broken into two components, vertical component, horizontal component. The S, okay, as a force can be turned into a horizontal component and a vertical component, and we've sort of talked through that as a process. But we have another set of forces occurring, because we can talk about the force, which is going to also be S, the tension in the other direction from the ring. We have again the mass m, creating the weight of mg, and we also then have a reaction to the tension created by that string S. So if you think about it, this ring here will move, okay, as a result of the tension that's occurring here, the horizontal tension in S, unless there's something acting in the opposite direction. So we have a normal reaction R there. So R in one direction must equal the horizontal component of S. So we can say that R is equal to, much like, we had a situation where this mass is not going up or down, so the forces up and down are equal. We can talk about this ring here not going left or right, so the forces acting left and right are going to be equal to each other. So if we appreciate that that is alpha, we're going to have S we're going to have S sine alpha. It's going to be, so that force acting horizontally, so is S sine alpha, and it's going to equal to R. We've also got the mg vertically. It's going to equal to S cos alpha. Okay, so you've got that activity going on there, as well as all of the forces occurring. So we've got T cos alpha going up is equal to mg going down. And then finally, we've got the centripetal force. We've got T sine alpha added on to S sine alpha is going to equal to the mass times by the radius times by omega squared. okay, for that circular motion of the mass that's fixed. So just mention that if the string is not sort of fixed at that lower point, if instead there's effectively a ring that in a sense could freely move, but it's going to stay in a fixed position, but because it's not fixed to that position, that tension is occurring, and there's a reaction on the vertical sort of pole that you might imagine it being, that ring sitting inside. The questions often talk about a wire going down. Okay, that wire is a wire that's effectively sort of fixed in place. It's like a strong wire. So, as I said to you, have a look at worked example 7.8 on page 131 to actually go through a question like that.